your application. It gives you powerful windowing capabilities that will handle even out-of-order events. It'll let you reprocess data easily. It'll do it with low latency, and it'll help manage any kind of accumulated state between rows. And so the key operations it's going to expose to you are, a lot like what you've seen if you've ever used something like the Java Streams API or the Scala Collections API. So Streams is a Java library. We haven't done libraries for other programming languages yet. But kind of the four key operations are something like map, which takes input streams and transforms them into output streams. Filter, which kind of takes input streams and filters out messages you don't want. Aggregate, which allows you to combine records that are coming on the stream to do something like a count or a sum or other aggregations. And join, which allows you to take a stream and join it to other streams or join streams to side information. So you can imagine, taking a stream of maybe customer interactions and joining on data about the customer. That's a common thing, and then maybe performing some kind of count on top of that by a dimension that is attached to the customer. So these are the types of more sophisticated things you can do really easily with this simple library. And the best part of this is, when you write a Kafka Streams app, there's really no additional moving parts. It's just a normal app. So, here is actually a complete Kafka Streams app in Java. It's basically just a Java main method. The first block there is going to have some configuration values that you would set to say, okay, what's the URL I'm connecting to for my Kafka cluster? How can I serialize my data? Then you're going to have a block that actually gives the transformation. So if I zoom in on that block, this example is basically doing word count, which is kind of the classic big data example. Now this is a streaming word count, so it's actually counting the occurrences of words as they come. So for each word, it'll say, okay, I have 1, I have 2, 3, 4, and it'll produce a continuous updated stream of how many of each word I've seen so far as they come in. And so this is an example of a Kafka Streams application. It's very simple, but it's doing something relatively sophisticated. And that example of producing counts to get updated, it's actually one example of how Streams allows you to unify the concept of tables, values that are getting updated with event streams, things that happened in the world. And this is actually, I think, the core problem in this domain of stream processing. It's something that isn't talked about as much when people talk about stream processing, but it's really, really core. I can't get into it in a ton of detail, but I'll kind of give an example of why it's so important. So I'm going to come back to this retail example I showed earlier. So if you think about how this works, I had this stream of sales that were occurring. So I'm selling products. I have a stream of shipments, new products arriving. I'm using that to calculate my inventory on hand. And that inventory on hand is a table that's getting updated, right? So I have these streams of things that are happening. I'm creating a table off of it. I'm using that combination of what's selling and the inventory I've got, and I'm using that to calculate when should I reorder, when should I change my price, right? And so this ability to process both tables of data, streams of events, and put it together in real time, that's kind of the core thing you get out of the Streams API. And very importantly, we talked a little bit about this ability to replicate updates, change logs, change data capture, and this Streams API works really well with this type of stream. So if you have streams coming out of databases, you can actually perform real-time computations on the stream of changes coming out of the database, and you can use it to effectively materialize a new view. So instead of taking the stream of changes from one database and recreating that exact same database, you can take the streams coming from many databases and join them together. So say that you had 10 databases, each of which had some information about your customer for different purposes, maybe in different business units. You want to create some kind of aggregate customer profile. You can use the Streams API to subscribe to these different streams and join together this kind of unified profile. That's an example of a kind of materialized view that you're calculating off this stream. And so this is something people don't always think of when they think of stream processing, but it's actually really important, this ability to create materialized views off of upstream stores. And in that example, I'm obviously going to be using both the streams and the connect API together, right? Connect is basically capturing data out of sources and getting it into destinations. Streams is basically performing the calculation. So these two facilities in Kafka work really well together. So now I've kind of walked through the 4 core APIs in Kafka. I've talked about producing, I've talked about consuming, I've talked about connectors, and I've talked about stream processing. So I've kind of talked about, how you can connect to the Kafka cluster. I've talked about the streaming platform video. What I haven't really talked about is some of the, non-functional characteristics of Kafka, like how it's implemented, how it works, how it scales, how it performs. And it turns out that that's, really important. I said I would address briefly this question of how does Kafka kind of compare to enterprise messaging systems, and I'll lead into it with that, right? A lot of messaging systems would talk about, connecting different things. They would talk about, building event-driven apps. How is this any different from that? In a way, it's not. I think Kafka is kind of an evolution of this area. But there are 3 key areas that I think differentiate things. So the first is around scale, right? This ability to operate a Kafka cluster at company-wide scale. The second is around the guarantees that Kafka provides. And the third is this much, much richer ability to build stream processing applications. So stream processing I've talked about, but the first 2, these are really about how Kafka works as a distributed system. And so I'm going to go just really briefly through that and give kind of an introduction to the characteristics of Kafka. For people who want to dive a little deeper, we're going to do a deep dive as the next talk on Kafka, as a data system and the guarantees it provides. But I'll just give kind of like a sketch of that so that you get something out of this introduction. So first of all, it's really important to be able to act as a kind of unified data pipeline that Kafka scale well and scale cheaply. So if you want to be able to use it for really high volume feeds like log events and stuff like sensor readings I talked about, it needs to be able to process hundreds of megabytes per second per server of throughput. You need to be able to store many terabytes per server. It needs to run on commodity hardware so you can add more capacity cheaply. And most importantly, writes need to be constant performance. So as more and more data accumulates in the Kafka cluster, it can't get slower. All of these are really important to any of the kind of big data stream processing workloads. If I didn't have this ability to scale cheaply, it wouldn't work well. And so in this respect, Kafka is really built a lot like a file system. It stores big blocks of data like a file system. It has the performance characteristics of a kind of distributed file system. As you append, it doesn't get slower. You can have many readers, and they're very cheap. And so this is a really important characteristic of it. The second is providing strong guarantees for data. So again, if you want to be a unified pipeline and you want to handle kind of core database updates, you want to replicate that to other applications or systems which are kind of critical, you can't lose data. You have to have very strong persistence guarantees. You have to also have strong ordering guarantees, right? If I have updates for a database that are being replicated through the system, I can't reorder them. The customer updates their account twice. They have a first update and a second update. If I reorder them, they may get the wrong final value. And so having strong guarantees and around both the ordering of data and the persistence and replication are really important. And that kind of ties into the next point, which is really how Kafka works as a distributed system, right? So by default, everything that's written to Kafka is replicated. So there are some messaging systems which support replication, but it's usually kind of a semi-untested add-on that nobody really uses. In Kafka, replication is always on. You can have a replication factor of 1, but that's not really a special case. It's just when you configure the replication factor to be 1. And effectively, nobody runs that way. Everybody runs with actual replication across multiple servers, which means that it's fault tolerant. You can have servers die, and you don't lose your data. You don't stop operation. You don't have to go update applications. Everything just keeps running even though one of the servers has died. Data is partitioned up over the cluster, so you can have topics and applications that scale well beyond the capacity of a single server, and you get that transparently as part of the abstraction Kafka provides. And you can scale the cluster elastically. You can add servers. You can spread out load. while everything is running without taking it down. And most importantly, the operation of the system is kind of decoupled, right, from the application. So you can have a central cluster that many teams use that you operate and add servers to and do upgrades on to new Kafka versions, all without bringing this down. So there are many Kafka clusters that have been in production for 4 years straight. And they've gone through many upgrades and they've gone through lots of maintenance and reconfigurations, but they don't come down for that. And that's a really important characteristic. So a lot of the people at Confluent came out of LinkedIn, and so I'll give a few stats about LinkedIn. LinkedIn is actually not the largest Kafka user anymore, although they are incredibly big and getting bigger at a fast pace, but they've been outpaced by a number of other companies that are also using Kafka at massive scale. But at LinkedIn, there's a representation of virtually everything happening in the company, from low-level operational statistics and traffic going through their network switches and application stats and error logs, all the way up to very high-level business activity and database changes. That means over 1.2 trillion messages written per day, which is, I think large even by the standard of crazy, outrageous big data stats. There's well over a petabyte of stream data that's stored in Kafka at any given time. The system is used by thousands of engineers independently, right? So, teams are able to kind of get their work done and interact with Kafka without filing a bunch of tickets and kind of waiting on stuff. It's a very kind of self-service system. And it's used by virtually every process in every data center, and either to produce or consume data. And it's used for even the most critical things. So in one of their newest projects, the distributed database that runs all their main data actually uses Kafka as the core commit log for every update to the database. It's in the critical write path, so it's used for very essential stuff. So, that kind of concludes my brief overview of the non-functional, characteristics of Kafka, how it works as a data system. If you're interested in that stuff, the next talk is going to dive into it in more depth. And that kind of completes this picture of, a streaming platform and Kafka, which, is built to be a streaming platform, and how it kind of operates, the problems it's trying to solve. I'm going to say a few words about Confluent. This is a company that I founded with some co-founders who also came out of LinkedIn. What we're trying to do is basically take that streaming platform vision and make it something that's accessible to companies, make it something that's possible to deploy for one app easily, and make it possible, to actually scale it to, run at company scale. And so what we're doing is really taking all the pieces we, either built when we were running Kafka or that we've seen other people build, and we're putting it together as a platform you can download that's open source and you can build against. So that is called Confluent Platform. It's available for free download on our website. It's basically a set of open source components that you can build against, without being locked in any way. And I'll kind of go through these really quickly. So we provide clients for different programming languages. So some of the stuff I talked about is just Java, but people interact with Kafka in dozens of programming languages, and we're putting together a whole ecosystem of clients and making sure that gets tested with each release. We provide a REST API for anything else if you want to have kind of REST interactions. We provide a bunch of the off-the-shelf connectors that I talked about. So if you want to connect to HDFS or JDBC databases. And then we provide facilities for managing schemas for your Kafka topics. So those are all the open source components that are part of our Kafka distribution, the Confluent platform. And then we provide a trial for our management tool, which is called Control Center. And that's available as well. If you're interested, it's it's part of the subscription, which gets support on this. So that's the Confluent platform that's available on our website. We think it's like really the best way to get started with Kafka. And that concludes my talk. So I'll give a brief preview of what's coming up next, and then I'll take a couple questions. So coming up next, we have a deep dive into Apache Kafka. This is really Kafka as a data system. What does it guarantee? How does it work? Consumer groups, logs, log compaction, replication. Will it lose my data? Will it not lose my data? How does it recover from failures? All that kind of stuff. This is going to be given by Jun Rao, also one of the original creators of Kafka and one of the founders of Confluent. After that, we have a talk on data integration with Kafka. So this is the data pipeline part. This is going to be all about the Connect APIs. It's going to be all about schemas and metadata, and how do you actually get all the streams or get them into Kafka and get them around. That's going to be by Gwen, who is kind of an expert in this area. After that will be 2 talks on stream processing. The first will dive in much more depth into streams, and that will be by Neha, who's Confluent's CTO and one of my other co-founders, and another original Kafka person. After that, we'll do an overview of a bunch of stream processing technologies, including streams, as well as a bunch of layers that can sit on top of Kafka. And finally, we'll dive into what does it mean to actually roll out Kafka in practice? What are the pieces you need to run this in production? What are the best practices for running Kafka, whether it's for one app or as a service for a whole company? And that will be given by Roger. So this is the upcoming set of talks. All of these talks work independently. So if you really just want to hear one of these, you care about stream processing but you don't care about anything else, you can just show up for that. If you watch them all the way through, you should get a really good overview of the area, which is kind of how we intended this series to work. So, thanks a ton for that. I'm going to take a couple questions now. I think David's been answering a bunch of questions as we went, so maybe they're all been wrapped up, but I'll take a few of these, and thank you for listening to this.
Yeah, thank you so much. I did my best to try to answer as many as I could online, and for those of you whose questions we don't get to today, Tracy and I will work to get answers back to you via email after the call is wrapped up. So 2 quick things in our last couple of minutes here. Where does the name Kafka come from?
Yeah, this is a great question. Everybody wants to know about that. I guess there's 2 theories for naming software pieces. One is give it some kind of really boring 3-letter acronym, like ESB. And the other is just give it some off-the-wall whacking in. We clearly went with the latter. This is something that was started as an internal project at LinkedIn, and we did have a set of names that were all based on Harry Potter characters. And then we ran out of good Harry Potter characters, and we switched to writers. And so Kafka, was on the list. And then we particularly felt like this whole area of data pipelines in particular and data integration and things connecting was particularly Kafka-esque. So I think that was probably the only real justification.
Okay. And then a real technical question as well. So how are keys mapped to a topic when the producer is generating messages and things?
Yeah, that's a great question. So I didn't really get into that just because this is such a brief overview of so many different things. But the key is optional. So you can have no key. You can just have a event, which is just the record with no key attached. But if you do specify a key, it will be used for partitioning data. And the guarantee we give you is 2 updates that are sent from the same producer that have the same key will arrive in the same order at the same consumer. And you might think, well, why do I care about that? And I'll give 2 reasons you might care. So it turns out to be very important in stream processing applications. It turns out to also be very important for any kind of updates that are being done to mutable data. So I gave that example of I'm updating a customer account, and there's 2 updates that you make. So first you change your email address to j@gmail.com, and then you change it to j.kreps@gmail.com because you realized you misspelled it or something. It's really important that I first, and let's say I'm replicating that into some search index or something. If I replicate them out of order, first I replicate the correct final spelling, and then I replicate the earlier misspelling, that search index is going to be permanently out of consistency with the original store. And so that ordering guarantee is really important. And this is actually a big difference between traditional messaging, which doesn't do a great job of maintaining order. Typically, data is ordered in the queue, but if you have multiple consumers, messages are potentially read out of order. So Kafka's model, I think, is better in that respect, in that we kind of shard up the data and give this strong ordering for each of these shards all the way through from producer to consumer.
Thank you very much. That's all the time we have today for questions. As I said, we'll get to those that we weren't able to answer right now online and via email after the call. Thank you all for your attendance, and have a good rest of your day.
Thanks, everyone. Hope to see you at the future talks. To a Kafka cluster. And a Kafka cluster is going to be a bunch of machines that work together to store these streams of data. So your app can basically write or publish a record. And these records that it publishes will be spread out over the Kafka cluster to allow the stream to kind of scale with the size of the cluster. And you can have many apps that all publish at once, and they can all write to the same topic if you want, or they can write to different topics. And so this is the producer API. The flip side to that is the consumer API, which, as you would expect, is doing the reads, right? It's consuming data. And so unlike reading from a file system where you might, do a read and then it's done, the consumer allows you to kind of keep reading as data arrives. So it can be very low latency, just a few milliseconds from something being published to when it arrives at a downstream consumer. And the consumer API is actually pretty powerful. In addition to letting you just read data, it actually allows you to scale out the consumption. So it's really easy to scale out writing. You just have more writers. But scaling out the consuming of data is a little bit more complicated, because you want to make sure that each update to a given topic goes to some process, and those processes could come and go. And so Kafka has an abstraction called groups, and for consumers they're called consumer groups, but these same groups are going to be used for the Connect API and the Streams API. And these groups basically are what help you do consumption of data. They make your Kafka topics multi-reader, so you can have multiple groups that all read the same topic. So maybe you write to that product view topic, and that gets broadcast to two different groups. So in this picture, I've drawn an A group and a B group. And you can think of each of these groups as being a kind of logical consumer, the A consumer and the B consumer. Maybe A is my Hadoop cluster, and B is some kind of real-time stream processing app, or something else. I don't know. But the key point is each event I publish, it will go to some process in the A group, and it will go to some process in the B group. And I could have any number of groups that subscribe to a topic. I could have 0 groups. I could have 100 groups. And within this group, Kafka is going to keep track dynamically of who's alive. So each process labels itself as being an A or a B or whatever it is. And if new processes, are started, they'll dynamically join the group, and they'll get some data sent to them to process. And if a process dies, so if a process, suddenly crashes, it's going to be taken out of the group, and the data it was processing will be given to the other processes. And this is a really important feature of Kafka that allows you to scale the processing of data to really large volumes. This is how you can, have really scalable consumption of data. And this group functionality is used not just for the consumer. It's going to be used for Connect, which I'll talk about next, and Streams, which I'll talk about after that. Okay, so that's the producer and the consumer, the kind of pub sub. This is stuff you would be pretty familiar with if you've seen messaging systems before. Kafka kind of generalizes the notion of a queue and pub sub with this group mechanism, which kind of gives you both of those modes as well as a generalization, so everything in between. So you can have, effectively, it's like pub sub with a queue of consumers at the same time. And, that's really how you would get apps integrated. So apps that are going to, intentionally read or write from Kafka. But a lot of things that you have are apps that are either already built or data systems. And these apps and data systems, they maybe have APIs already. And those APIs are passive, right? So maybe the app has a read API or a write API. Maybe a database has a read API or a write API. It doesn't work with Kafka. It doesn't know about Kafka, right? If you have a relational database, most likely that relational database is not writing to Kafka. It just has an API for doing updates and selects. And so how can you integrate something like that that's passive with Kafka? And for this, Kafka has what's called the Connect API, and you build what's called a connector. And you can build a connector that is totally off the shelf. So, you can build a connector for a relational database, which is reusable. And that's what this Connect system does. So you have the concept of a data source, which can be an application or any type of data system. And Connect will allow you to run a connector which continuously reads data into Kafka and publishes it to a Kafka topic. And it will also allow you to build a connector which works the other way. It reads data out of Kafka and continually writes it to a destination, a sink. And so these connectors are kind of like almost the inverse of the produce and consume APIs. It's like a producer that pulls data out of the source and a consumer that pushes data into the sink. And this is really important if you want to roll out Kafka and get access to a lot of the data you already have in existing systems. And it's really important if you want to build data pipelines using Kafka, because this will give you a reliable connection to these systems. And so you might say, well, why do I need this? I could just use the producer and consumer APIs in Kafka. And the answer is the Connect framework and the Connect APIs will really help do a lot of the hard work. So it will help you build a connector which can scale out. It will make these connectors fault tolerant so that, if the process fails, it will be taken over elsewhere. It will allow you to manage a bunch of different connectors centrally, and it will allow you to capture data about, capture schema information with your data and propagate that along as well. And this is a really important area I'm not going to be able to get into in huge detail, but it's an incredibly important part of building these types of data pipelines. We'll get into this more 2 talks from now, where we talk more about the data pipeline area and we get into the best practices for building streaming pipelines. So I think the best way to illustrate some of this is just go through a couple of examples of how the Connect APIs work by talking about integrations that actually exist, that are off the shelf, that you can download and use for real data systems that are common. So the first would be something like Hadoop, where you there's a lot to talk about and almost a whole worldview that goes along with it. And so what we wanted to do, instead of just giving, a talk here and a talk there on different subjects as they kind of came to us, was kind of organize things a little bit more and walk through the area in a more disciplined way. And so this talk is going to be kind of an introduction to the area. So I'm going to try and talk about what are the problems that Kafka is trying to solve, and what is it? What does it do? And so this is the first of these talks. I'll give some pointers to the stuff that's coming up when we're going to dive a little bit more depth into different areas, and I'll give an overview of the schedule of things that are going to come after it. But let me start by just kicking off kind of the question we're trying to answer, which is, why streaming? Why do we need a new thing? What is all this streaming data stuff? What's stream processing? This is really the area that Kafka is attacking. And so rather than just kind of getting into it and going through a list of Kafka features, I'm going to start and try and motivate this. So to do that, let me actually kind of go through the architecture I think is common for most applications and most companies. So the first thing most people are probably familiar with is request response apps. So this is kind of web apps, HTTP services, things that take a request and give a response. They usually, happen quickly. So maybe you have a second to do your processing, maybe a lot less than that. This is the domain of OLTP databases, key value stores, HTTP services. And this is kind of like the main tool in the toolbox for building applications. When most people think about building an application, this is what they're thinking about. And it's inherently synchronous. Like when you send a request, it's not done until you get the response back. And in a lot of cases, this makes sense. If you're displaying some type of UI, you can't actually display the UI until you get the data that needs to be there. So if you send a request to a web server, you have to get back the contents of the page before you can print it. It's a little bit obvious. But there is another thing, usually in the back, kind of in the guts of a company, which is kind of the offline world, right? This is batch processing. This is stuff that happens maybe once a day is most common, but maybe once a week. Occasionally more frequently, but usually not much more frequently. And these are, big systems that are going to suck data out of, all the online databases and maybe churn through it once a day. And so maybe these are kind of the two main tools in our toolbox if we're writing computer programs. These are the two, main areas that they run. What are the problems with them? Why do we need any kind of new thing? Where does Kafka fit into this? Where does, streaming fit into this? So I'll try and talk about, first two problems that I think are left unsolved in these two setups. And the first of these is pipeline sprawl. So this is how data gets around. So I showed like a really simplified picture with a couple apps and a couple databases and, a small warehouse area. But the reality is much more complicated than that in any company, and especially in any large company. It's impossible to depict on one slide, but there's going to be caches and search indexes and, dozens and dozens of databases, maybe hundreds, maybe actually thousands, depending on the size. and they're all kind of interwoven in complicated ways, right? And this, gets worse as a company splits into business units, and it gets worse as more technologies are adopted. So you often end up with a situation where kind of in the limit, everything is connecting to everything else to kind of integrate data, and it's doing it in a one-off way. So you end up with, almost something like, n squared different data pipelines for different types of data and different applications. And this is just inherently complicated and hard to manage. And so this is this first problem, this kind of data pipeline sprawl. How does data get around? And the second problem has to do with the nature of these services, these request response services, and their limitations. So if that's our default way of implementing things, the problem with that is it's inherently synchronous. Like you send a request and, it processes and it gives a response. And so even if you're using something like non-blocking I/O or doing things in parallel, you're going to have a situation where you're doing a bunch of things synchronously. Or if you kick it out of this domain entirely and you put it in your batch domain, then you're going to have something that's like very asynchronous, like once a day. And so this is really the second problem, is synchronous services. So if it's microservices, maybe there's one service calling out to other services, and you're kind of waiting on all that to complete. And if it's a monolithic app, then it's all in one big glob, but it's still a bunch of things happening that all have to complete by the time the request is done. And so these are the two problem areas I'm gonna get into. So first of all, how can we solve this pipeline sprawl problem? And second of all, how can we actually build services that are truly decoupled, that aren't part of this huge set of things that have to happen? And I think this is actually really important. So I'm gonna give an example, and I'll come back to this example a number of times, which is retail. So if you think about how retail works, you have something which happens synchronously, like a sale. So I give you money, you give me a product. That's a very synchronous interaction, right? But a lot of the back end of what's happening in a retail business is dealing with shipments that arrive, adjusting your inventory, reordering things that you're selling out of, maybe adjusting your prices as you sell out of it, doing analytics and fraud. There's this whole back-end machinery to a retail business that's completely decoupled from the synchronous interaction with the customer. And this is why being able to model that in some way is important. And if the only way we have to model it is to take it completely offline and do it once a day, that's a very odd schedule for computers to work on. Once a day is kind of, I get up, I drink my coffee, I look at a report. That makes sense because I'm a human being and I sleep at night. But a digital business and computers don't sleep. They work continuously. It doesn't really make sense that they would be on a schedule tied to when the sun comes up. So being able to have some place where this bulk of logic that's happening asynchronously is the other problem. I think it's really important. I think when you look at most businesses, a huge portion of what they do, maybe a third, maybe 50%, is in this kind of asynchronous domain, but it's not really very well supported by the technology platforms we have. And so I'm going to argue that this is really the two kind of key uses for streams. So the first is building data pipelines, like getting data around, put it in a stream and ship it from place to place. And the second is building these types of asynchronous services that react to the stream of data, that process the stream of data, or transform the stream of data. These are really the two, use cases for this technology. And I'm gonna try and outline this in a little bit more detail so you get kind of a feeling for the problem. Then we'll dive into Kafka and how it actually solves it, how it makes it possible. So the architecture that we have in mind is a little different from that picture I showed before. It's an architecture that looks like this, where you have some type of streaming platform that's able to integrate a lot of these data systems and applications, right? So it's solving that kind of n-squared integration problem by putting something in the center that's able to hold these streams and connect them without everything having to directly connect to everything else. So each system or each application just integrates with a single thing, and that connects it to everything else that is connected. And secondly, it's a place where these kind of asynchronous applications can hang off of it, and they can do processing asynchronously from the main request response cycle. So it doesn't replace request response apps, and it doesn't replace batch processing on the back end, but it really serves this kind of asynchronous near real-time area. And this may look really familiar to people. It's not that different from the pitch for messaging systems or enterprise service buses or a whole other set of technology that's been around for a while and is maybe even a little long in the tooth. And I'll get into that briefly towards the end. What's the relationship of that stuff to Kafka, and how do we think about that? But for now, I just want to put the problem out there, and I'll introduce it almost from first principles. So let me start by diving into this problem of data pipelines. So that was the first area I brought up. So let me try and explain almost the mentality of how to think of data pipelines in terms of streams. So particularly in terms of event streams. And I'll start with this bold claim that you can really think of all your data as being streams of events. And let me try and back that up. So obviously I can't go through a catalog of all the data you actually have in your company, but maybe I can give an example of a few types of things and how they map to event streams. And let me start by just saying what I mean by an event, and I'll get into it in a little bit to say what I mean by a stream, and that'll make it more concrete. So by an event, I really just mean a message or a record. So a record, something with fields. It doesn't really matter how it's represented, but maybe an example of this would be in e-commerce. Maybe somebody views a product. Maybe they view it on a web page, and you could record that, and it would have fields, and those fields would have values. And in this case, I've kind of shown it as JSON. It doesn't really matter the format of the data. This is what I mean by an event. And kind of the magic of events is that they're a little bit different from requests and responses. Like when I make a request to a service, I'm saying, hey, fetch me this data, or hey, store this thing. And the response is going to be like, okay, here's your data, or okay, I stored it. But an event is a little different. It's just a fact about the world. So this event is saying, hey, this product was viewed. A different type of event could be a sale that occurred. It's just a fact that says this happened. And if you can subscribe to these events, if you can tap into these streams of events, they're going to have two really interesting use cases. So the first use is like as data. You can compute things off of this. And the second is going to be as a kind of trigger. You can make other services react to what happened. And I'll dive into both of these to kind of say what I mean. But this is what I mean by events. So how does this map to actual data you have? Well, first of all, an obvious example is something like a log file where you're recording a bunch of things that happened. So a request log like this Apache log I'm showing, that's kind of an obvious example of events. Each of these lines is a type of event. It's recording data about what happened. It may not be a super interesting stream of events, but it's a stream of events. And the fact that we're storing it in a log is almost incidental to what the data actually means. The next example, which is slightly less obvious, is something like sensors. So by sensors, I just mean some reading of the current state of some measurement, right? And this comes up a lot in IoT use cases, in logistics, maybe vehicle positions. But it even comes up in software all the time if you do any kind of monitoring. Like your application may have counters or gauges, and you can kind of take the current value of these. And this is how any kind of monitoring system works, as a stream of these readings from your app. And it might give you time series information about the number of requests per second or something like that. So that one's not too surprising. Let's get to something now that's really different that I think can be represented as a stream of events, and that's databases. So this one I think isn't obvious at all. When you think about databases, you probably don't think about event streams. You probably think about something like tables, right? And what I'm going to try and do is actually show how databases can be seen as a stream of events. And this is something that is often called the table stream duality, which makes it sound a little bit fancier than it is. So if you ever want to impress somebody, or you want to think of one smart thing you learned in the course of this talk, you can say, well, I learned all about the table stream duality, and even if you snooze through the rest of it, you will have learned that. So this is what I mean. So when you think about a table, you think about kind of a rectangle, right? It has columns and it has rows. And so my table here is just going to be simple. It's just going to have a primary key and a value. In reality, the key could be made of many columns and the value could be made of many columns, but it won't really change anything, for my purposes. And the thing that's different about this table than a lot of those other event streams I showed is, this is actually only the state of my table at one point in time, right? So tables are getting updated all the time. They're changing all the time. So how can I represent my table over time the way that that log file was kind of being appended to over time? And if you think about this, this is kind of the key problem for a data pipeline that needs to replicate data in a table. And one way to do that might be to snapshot the table. So I would take a snapshot of my table at time 0, and maybe it has 1 row, and I would take a snapshot at time 1, and maybe it has 2 rows, and maybe I take a snapshot at time 2, and it has some different rows, right? And if you think about all of these, snapshots or dumps of the table, it's a little bit inefficient, right? Because I'm capturing a bunch of rows in my database. Maybe my table has, 1 million rows, but maybe only a few of them change. So if you wanted to make this more efficient, you could just take a diff, right? Instead of dumping the whole thing, I could just say, give me the rows that changed. And if I made that process of dumping the table more and more frequent, that diff would get smaller and smaller, right? The number of rows that changed would get smaller and smaller until it got down to finally kind of the limit of 1 row. And if you think about that, what that sequence of rows that change, that's basically the updates. It's like a sequence of like put operations, or either inserting a new row or updating an existing row. And that sequence of puts, that's basically a stream, right? These put operations are like immutable events, and the event is something like the value for this key is now this. And if you had that sequence of updates, you could take it and you could replicate it between different systems. And I could take it out of one database, I could replicate it into another database, and I could apply those updates on that new database, and I would have the state of my original database there, and I could keep it in sync. And I could do that either at the end of the day, or I could do it in real time. And so this is actually less obvious, but this is an important point, that databases, these kind of mutable data stores, it doesn't need to be a relational database, it could be a key value store or something like that. This can also be represented as a stream of events. And this is actually not something I made up. This is a common thing in change data capture for relational databases, where you have a system which basically captures the updates or modifications to the database and allows you to replicate it around. But as we talk about streams and as we talk about Kafka, we'll talk about making this much more general than just creating an exact copy of your Oracle database in another Oracle database. We'll talk about being able to process these streams and so on. And so that's really the key insight for this data pipeline problem, is the idea that you could represent your data as events, that would apply to many different types of data and would work for many types of data systems. And you could kind of have a universal pipeline, which is the event stream. And the idea we're leading up to here is kind of what I showed in the architecture diagram, that you could have some type of streaming platform, and it would integrate a bunch of different types of data systems or applications, maybe relational databases, key value stores, caches, monitoring systems, analytics, search replicas, offline things like data warehousing or Hadoop, and that all of these could feed off of this central platform that would have your event streams. And this way of thinking about data is actually a little different. So I'm going to walk through an example that I think kind of gives the benefit of it. I'm going to use a Clickstream example, but this would work for any type of event stream. We talked about how there's lots of things that can look like events once you kind of understand that way of thinking. So I'm going to use an example of a web application and products being viewed. And so I used this product view event example before. So in the simple case, maybe my web application is just producing this stream of events. Maybe it produces it to this streaming platform, this thing in the middle. And I'm not going to give it away, but obviously the thing in the middle is going to be Kafka when we come to the Kafka part. But for now, we'll just say it's going to this streaming platform. And from there, maybe my goal originally is just to get that data into Hadoop, where I'm going to do some analytics. And the only real advantage in this picture of the streaming platform is, well, it's up all the time, and so I don't have to be dependent on Hadoop being there at the particular time I want to publish events. And the web app isn't really tied to the particular analytics platform I'm using. So maybe I've decoupled these two things a little bit, but ultimately it's just kind of a pipeline, a way of getting data from one place to the other. But where that starts to really become valuable is as more things use that type of data, right? And this is common in any kind of big organizations. Maybe the only way to view products isn't this web application. Maybe it's also possible, or becomes possible in the future to view products on a mobile app, or maybe there's APIs which give the same data, and they also need to record similar things. And the nice thing now is that all of those can just publish to this stream of product views. And the Hadoop cluster doesn't need to know about these different types of applications. It doesn't need to go integrate with them. The team that works on Hadoop doesn't need to like have a contract with each of these teams that makes these different apps. It just kind of sucks in the product views from the streaming platform. And likewise, these different apps don't really need to know about Hadoop. They're just sending it to the stream. And this gets even more valuable as that data becomes more important and gets used more. So you can imagine a lot more uses for these product views beyond just Hadoop, right? So you could imagine that, you know, we want to have security measures around this so people don't scrape our web app. Maybe we want to have some kind of recommendation engine that tells us, hey, people who viewed this product also viewed this other product. Maybe we want to do some kind of analytics on top of this to say, you know, yes, people are still viewing products on our different applications. And the key advantage now that the streaming platform is giving us is each of these people who want data don't need to know all the places it comes from. And the places who produce data don't need to know all the places it goes to. And you know, new sources can appear at any time, and new destinations can appear at any time, and they don't all need to coordinate. And this is a really important thing in a larger company. And you know, it's nothing revolutionary. You know, in a sense, it's just pub/sub messaging. But I think, you know, really doing it for real at large scale is actually kind of the hard part. And I'll come to, you know, some of the things that make that possible. So this is really this data pipeline use case, and this is the first use case, is being able to get data around using this streaming platform and using event streams. Now I'm going to come to the second application, which was, you know, how can I build asynchronous applications? How can I do that well? How can I make that easy? How can I make it as easy to build an asynchronous service as it is to build a web service using request response? And that is the area of stream processing. So we talked about event streams for data pipelines. Now let's talk about them for processing, for apps, for business logic, for you know, things your company does. And to introduce that, I'm going to walk a little bit more into these different areas we talked about a second ago. So we talked about request response, we talked about batch processing, and now I'm talking about stream processing. Let me try and show a little bit about how these fit together. So, you know, request response processing, I think most people know, you kind of send the request and you get back a response. And so, you know, it's kind of one input gives you one output. And, you know, you would never think about it this way, but when you write a web service, it doesn't process past requests. You just start it and it processes requests that come in the future. And that's so obvious that you would never say it, right? But now if we switch over to batch processing, you know, it's a little different. So instead of getting one request and producing one response, it kind of gets all its input all at once. And it gives you all the output all at once. And unlike a service, which kind of comes up and processes things that are going to happen in the future, a batch process inherently takes a bunch of data that's already been recorded from the past and processes it all at once. So batch processing is kind of inherently about the past, right? It processes things that already happened. And what's interesting about stream processing is it actually generalizes these two things. So instead of getting one input, like request response, and producing one output, or getting all your input and producing all your output, stream processing is going to allow us to have more flexibility here. It's going to allow us to say, look, I'm going to take some inputs and I'm going to produce some outputs. I might take one input and produce one output, or I might take a bunch of inputs and produce a bunch of outputs. But I, the program, have control over that. And in addition, it's going to allow us to generalize the time. So now, instead of having something which just goes and processes the past, like the batch process, my stream processor can process past data that's been stored, but it will like keep processing into the future. So as new data happens, as values evolve, my program will adjust to those and evolve and take them into account. So it really generalizes these two areas that we talked about, and that's what makes it so powerful. And so another way to think about this, which makes it a little bit less, you know, mystical, is that a stream processor, it's really just a type of event-driven microservice. So it's, you know, it's a little app that is going to be able to process streams of data. And you know, I'll plug it into this retail example that I gave before. So if you think about it, sales are probably something that's going to be request response. It's really a synchronous operation. You give me money, I give you your product. But a lot of the other things that are happening in this picture are going to be really asynchronous. These are going to be these kind of event-driven microservices potentially, right? So price adjustments, right? When do I need to raise the price on something? Well, I need to do it as it's selling out. So I need to, adjust to the sales and the shipments. I need to compute the inventory I have on hand. If that gets low, I probably want to reorder, and maybe I want to raise the price a little bit. And I want to do that quickly so I don't sell out of all the the products I have. And so you can really view a lot of things that are happening in a business. In this picture, I think a lot of the price adjustments, a lot of the reordering, a lot of the analytics and fraud stuff, some of the inventory adjustment processes, you can really think of this as being things that are reacting to this stream. You can think of it as a type of stream processor. And that plugs back into this central streaming platform vision that I talked about. In addition to having data pipelines that are built on streams, you can have applications that also feed off of this event data that reacts to things that happen, that process it. So I've drawn apps and I've drawn stream processing here, and they're really kind of the same to me. I don't see a huge difference. So that's kind of the lead up here. This is the problem domain we want to be able to solve. And the question is, how can we build this? And there's no surprise now that this kind of streaming platform is Kafka, right? And this is the motivation we had in building Kafka. These are the use cases for it. So now I'm going to walk through a really brief introduction to Kafka, what it's good for, what it does, and why we built it, and how you can kind of use it as a streaming platform. So I assume people who showed up to this have some knowledge about Kafka. It's an Apache project. It's open source. It's used in production at really thousands of companies now. So it's been really successful as an open source product, which we're really proud of. But now I'm going to kind of walk through it just from scratch and give people an introduction to it so they can get a feel for what it does and how it solves the problems I talked about. So I'll start with the data model. So Kafka is fundamentally about events or records or messages. I'm going to use those terms sort of interchangeably because in this area people kind of use these different terms and they kind of all mean the same thing. But in Kafka terms, a record or an event, it's basically a timestamp that is when the event occurred. It's a key and it's a value. And the key and value are byte arrays, and you can put any format of data you want there. Kafka is not opinionated about the data format. In your company, you probably would want to have some standard that you rely on. The key in this case is used for partitioning data up in the Kafka cluster. I'm not going to dive into that in huge detail. And the core abstraction in Kafka that is used to represent streams, like I've talked about streams in a very kind of loose way, but what does it mean when you represent it in a data system? The core abstraction in Kafka is this idea of a log. And by log, I don't mean like an Apache log here. I mean something more similar to a commit log, like a structured log, which is a sequence of those records. So the data structure that Kafka is maintaining is a sequence of these records. So and each record has a unique number called an offset, so 0, 1, 2, 3, 4, etc. And writes are appended to this log. And readers can basically, read the log however they choose, really, but they would usually read from left to right. And it turns out this is actually, a pretty good basis for publish-subscribe messaging. So, you can think of the writer as producing a stream of events that are appended to the log, and you can think of these consumers as subscribing and reading along in real time. And allowing that to happen is kind of, the core abstraction in Kafka. And we'll talk about the different APIs and ways to access it, but under the covers, this is the core thing Kafka is maintaining. And this works really well for the type of mutable updates I described, right? So it'll work really well for changes to databases, right? And that stream of updates. And Kafka has special support for maintaining that type of data that's a sequence of updates to records. I won't get into this in huge detail, but the next talk is going to get more into the internals of Kafka, and it will talk more about how Kafka deals with this type of data. And so the fundamental abstraction in Kafka is built on these logs. It's called a topic. And so a topic is like a named feed of events, and it's really just a partitioned set of logs. So, we've basically taken that log and we've sharded it into a bunch of partitions or shards, and we do that for scalability and to spread data over the cluster. rights are appended to the end of these logs, and subscribers subscribe to them. This is the fundamental abstraction in Kafka. And then Kafka gives you, in addition to like being able to replicate that and store that in the cluster, which I'll talk about, it gives you 4 core APIs for interacting with these logs and for interacting basically with streams. So these APIs are the producer, the consumer. These are going to let you basically write and read data. The Connect API, which lets you write connectors which integrate off-the-shelf systems, and the Streams API, which lets you transform or react to data streams. And I'll go through each of these in a little bit of detail. For the producer and consumer, I'm not going to say too much because they're relatively simple. They're complex to build, but they're simple to describe. So the producer is really straightforward. It basically